Okay, now it's perfect.
Can you see my presentation?
Yes.
Now?
Yeah.
Okay. Thank you very much for the opportunity for present my work. I am Gerardo, and I am a PhD student in Mexico City. And I'm going to talk about 3D numerical simulations of structure longer jets. These jets start its propagation within a massive star progenitor. Okay. In the past session, Leo told us many properties of gamma ray burst. In my talk, I focus on the jet dynamics. The jet is the mechanism to produce a high energy flux in gamma radiation, and even the jet could explain the high variability in light curves. For my talk, I focus on the longer Bs, which are powerful relativistic jets. In the first seconds, its propagation is into this massive star, and also reach the breakout. And in the future, the jet can emit in gamma radiation and more and far away produce the afterglow radiation. Previous studies of longer Bs have been performed in both analytical and numerical form. Numerical simulations provide us a well understanding the jet dynamics. For example, in this density map from Lopez Camara 2016, you can see the evolution of relativistic jet with which start its propagation into a massive star. And once the jet gets the surface of the star, reach a breakout, and the external cocoon form external cocoon, and the working surfaces are a product by variability source of the jet, and this working surface probably are the responsible for the gamma radiation when start is shocks between them. On the other hand, I put this picture, and the idea is show you that the different jet launching produce different jet morphology. Why is important to study the jet morphology? Because when the jet reach the breakout, the start produce a cocoon, and the cocoon it's responsible for the afterglow emission, for example. And in a previous study, we found that different jet structure produce different light curves from numerical simulations. This is a 2D map of energy in 2 dimensions, and basically in the left side, the jet at the launch point, the jet these jets in the left side, its energy was dominated, its kinetical energy was dominated at the launching point, and in the right side, the pressure was dominated at the launching point, and there are substantial difference between them. And also for this work, it's important also to remark the stability of the jets. For example, in this map of final velocity from Gottlieb 2020, in the upper panel, you can see a non-stable jet, an unstable jet. The material of the jet is fragmented while the jet tried to drill the dense media, the very density media of the star. And this turbulence implies that the material of the jet is mixing, and a lot of energy is expended in this process. This implies that this jet is non-successful jet, and is a not good candidate for produce longer Vs. And these people implement a weakly magnetized jet and get more stable jets whose propagation is it's very fast and more stable. In the next slides, I want to show you that also our implementation of our initial conditions also produce stable jets without necessity of to implement this weakly magnetized jets. Okay, what is our motivation? In the previous studies, had considered jets injected with a top hat structure. The top hat structure is like this dashed line in this cartoon. These kind of jets have all its energy concentrated in a small region that is a core, and the projection of its velocity is in one direction, in radial direction. I will consider jets injected with different structures at the launching point. For example, there are some works about jet launching that they found that in the first milliseconds of jet propagation, very near to the central source in the central engine, the jet have a structure, initial structure. And the point of this work is, okay, take this hypothesis and implementing in our initial conditions far away of the central engine and start the propagation of a jet with an initial shape. And what is the implication in the jet evolution during its propagation into the star? Okay, what about of our initial conditions? We perform our numerical simulations in 3 dimensions in the Mescal code development by Fabio De Colle in 2012. This is an example of all-star region. However, this kind of simulations expend a lot of computational resource, and for this reason, and our computational time was limited. We implement a special initial conditions in order to do more faster of our simulations. This is take only the region where the jet will be propagating, and implement adaptative mesh refinement in order to resolve with a good resolution the jet channel and the propagation of the jet core. Okay, the main properties of the jet is the launching point. It's at 10 to 9 centimeters with an initial Lorentz factor of 5 and a jet opening angle of 10 degrees. And we implement the jet structure through a function which depends of angular theta measured from the theta, the z axis, and we implement this behavior through the luminosity, which depends of angle and the projection of velocities of Lorentz or Lorentz factor. In addition, we implement a variable source and perturbations in the density of the jet of 1% in order to break the jet symmetry, and precessions around the z-axis. Also, we perform a simulation of supernova. It's like to the presentation of yesterday from Fabio De Colle. Okay, this supernovae is launched 1 second after the jet launching, and the energy is 10 to 15 ergs. Okay, this is an example of jet propagation in 3 dimensions. The jet in the left side is propagating without supernovae, and for this reason is more faster. And okay, the jet propagating into a supernovae, it's more slower and have a different shape respect the jet of the left. Okay, this is a map of Lorentz factor. It's a code of 2 dimensions. And I want to show you different point of view with a different jets, with jets launched with different energy at the initial conditions. For example, these jets was dominated, its pressure was dominated at the initial point. And in this case, we obtain jets, very turbulent jets, and the effect of the variable source is viewed with through these lobes. Also, okay, we have the top hat, a comparison between top hat jet and Gaussian jet, and basically the shape of the jet are the same. Is the same. Only the difference is in the velocity. The Gaussian jets are more slower, and in the other hand, the jets whose kinetic energy dominates the launching point are more faster jets. And we found that these jets get more collimation and also are more stable during its propagation. And in addition, the effect of variable source are dilated. And it's important to remark that these jets are faster than the pressure-dominated jets, and the collimation it's important in this case because it drills more easy the dense material of the star. And finally, this is the case of a more realistic case. This is the jet propagated into the supernovae. The supernovae was launched 1 second before this jet, and swept up the dense material of the star, and the jet start its drilling in a low density. And for this reason, the material in the center of the jet is more faster. This is important because in the first slide, I told you that we need to avoid turbulent jets, and the speed of this jet is more turbulent. However, the faster material remains drilling the dense stellar media, and probably this is a good candidate for a successful jet. And this is the distribution of the energy, the total energy of the jet. Basically, this plot shows that the different structures have a superposition, cannot be distinguished between them. This is the kinetic dominated jet, more collimated. The pressure dominated jet, it's more expanded. This is the energy. The jet propagating into the supernovae, which expends much of its energy during the propagation into the supernovae. And this is an interesting case. We perform high luminosity jets with a luminosity of 10 to 52 ergs. And in this case, the structure can be distinguished between them. Why is important this kind of plot? Because in the future, once of the jet reach the breakout and expand its cocoon, this distribution of energy is important to do the calculus of afterglow radiation. Such is an example. We recently published this kind of a study changing the initial conditions of the structure of the jet, but in the case of short gamma ray bursts. And we found that the different shapes of the cocoon after the breakout produce different light curves. And this is implications from the implementation of initial conditions with structured jets. And finally, my conclusions are we perform numerical simulations of top hat and structural Gaussian jets in 3 dimensions. And we consider three scenarios: jets whose pressure dominates at initial launching point, structured jets plus supernovae, and kinetic energy dominated jets. The most important results are the next. For a dense media, this is the case of long GRBs. The initial structure is washed out, except in the case of the high luminosity jets. For a tenuous medium, this is the case of short GRBs. The initial structure plays an important role in the jet evolution and have a strong implication in the future light curves at large scales or afterglow radiation. And the presence of supernovae affect the jet evolution, changing the breakout time and the jet acceleration. That's it. Thank you very much.
Thank you, Gerardo. Excellent talk. Questions? Please raise your hand. Jean-Luc, please.
Thank you, Rosa, and thank you for the talk. My question is about a very luminous gamma ray burst. We have not seen any gamma ray burst with an isotropic energy larger than, say, a few times 10 to the 54 Hertz. Of course, this is enormous, but what do you think could limit the energy radiated per solid angle to this kind of value? Because I have seen in one plot you have shown you go up to 10 to the 55 and above. Do you think that is it the energy injected in the jet which limits the observed EISO or something else?
Yes, we consider the isotropic energy of 10 to 52 ergs, and divided per solid angle is 10 to 15 ergs. And actually, our case of very luminosity jets could be not observed yet. Yes,
but there is no, I mean, there is no physics in your study. There is no physical mechanism that could limit this energy. This is only maybe the injected energy or something like that.
Yes, yes.
Okay, thank you very much.
More questions? Fabio, do you want to comment something? No. Okay. If there are no more questions, we can move on to the next talk. Please, Kim.